Thank you for joining another exciting vibration research webinar. In previous webinars, we have discussed how to gather good vibration data, correlate it to real-world service life, and use it to develop a good vibration test profile with the fatigue damage spectrum FDS analysis tools in vibration research software. Today, we are going to take it one step further by talking about vibration sampling plans and why you need them to ensure robustness in your product. We will explain what a vibration sampling plan is, the math behind the Weibull success run formula, and how to apply it to your particular vibration test. Doing this will not only make your vibration tests more meaningful, but will also provide realistic insight as to whether your product is ready for release to commerce. Please feel free to use the chat feature to let me know if you have any questions or comments during the presentation. Your feedback and questions are much appreciated, and we will be sure to get back with you after the webinar. My name is Tom H. Atz, and prior to working with vibration research, I spent many years, decades actually, working in validation testing of automotive components. When it came to solving complex vibration problems, I always found that vibration research was ahead of the pack in innovation, collaboration, and support. The people at VR have built a great company and are ready to help you make your product better with shock and vibration testing done right. Since VR's founding in 1995, the company has brought many innovations to the vibration testing arena. Field data replication allows for the one-to-one replication of field environments in a non-iterative process, allowing tests to reach full level quickly, saving our customers time and money. Kurtosion is a patented technology that adds the effects of real-world kurtosis to a random waveform. This allows peak accelerations to reflect the real world, even around resonances. The fatigue damage spectrum generates random vibration tests based on field data, thereby approaching a real-world environment as closely as possible in an accelerated testing timeframe. IDOF, or instant degrees of freedom, improves the accuracy and reliability of the short-duration random tests commonly used for expensive launch systems and complex payloads. It uses an advanced and patented algorithm to deliver accurate and low-variance PSD estimates, calculated much quicker than traditional averaging. IDOF removes the estimation error while displaying the control error, providing the true difference between the PSD of the signal and the demand. STAG, or sign-on-random test generation, is specifically for developing vibration tests for products that live in environments with dominant sinusoidal content, such as engines. STAG ensures that all forcing functions are realistically replicated for the correct duration during your vibration testing. Most recently, TrueClip was introduced to reduce high sigma peaks on the shaker table. This clipping method applies to the control measurement and minimizes the chance of exceeding maximum acceleration, velocity, or displacement limits on your shaker. These are vibration research's most noteworthy innovations, but our products exhibit hundreds of other innovations covering math algorithms, usability, and user interface features that allow users to confidently develop and execute vibration tests efficiently and with meaningful results. The VR9500 is vibration research's best-selling control hardware for vibration and shock testing. It is scalable to 128 channels, and its features include a sample rate of up to 200 kilohertz and 2 outputs. The VR10500 is our high channel count control hardware for vibration and shock testing. It is scalable to 512 channels, and its features include a sample rate of up to 256 kilohertz and 4 outputs for multi-shaker testing. Vibration research controllers have a high-speed RISC processor that can process large data sets and efficiently run vibration tests at low and high sample rates. They are compatible with all electrodynamic and servo-hydraulic shakers. The VR9500 and VR10500 also function as data acquisition devices. The Observer 1000 represents a new generation of technology for field data collection and analysis. Designed for mobile use, it is compact and weighs just 1.5 kilograms. It is also battery powered and has an integrated SD card for data storage. The device supports test configurations with up to 16 channels using a smartphone or tablet via wireless connection. After setup, users can monitor and control tests wirelessly or let them run autonomously. We also offer a small collection of low-force shaker systems sourced from various manufacturers. So let's talk about vibration sampling plans. A vibration sampling plan simply states how many repetitions of a vibration test profile that represent one product service life must be repeated for a given number of samples on a test to demonstrate a particular level of reliability and confidence level if 0 failures are found during the duration of the test. They are most applicable to product validation at the process confirmation stage, but can also be used earlier in product development to aid with reliability growth, modeling, or as part of a product screening after production has started. While testing multiple product samples to failure with a field correlated test profile is the best way to predict reliability, this is not always practical due to time and/or lab equipment considerations. Sampling plans are based on demonstrating reliability by testing a predefined number of product samples for a set duration with no failures. This is called a success run test. To develop a vibration sampling plan, good data is essential. Ideally, good data is measured on the product while in use in real field applications. If this is not practical, due to not having prototypes available or lacking suitable data acquisition hardware and knowledge to make measurements, or not having accessibility to a representative environment to record good data, then surrogate data from a similar application or from past experience or from an industry standard or online source is next best thing and can still be used. Vibration research makes a great portable economical data acquisition system, the Observer 1000, that can be used to gather good data. Vibration research ObserView software can then be used with this good data to process the data into a good field correlated vibration test profile with correct frequency content, amplitudes, kurtosis, and duration. The resulting test profile should represent equivalent vibration exposure to one service life of the product, ideally as defined in the product's technical specifications. The best way to develop this profile is to use Vibration Research's Fatigue Damage Spectrum, or FDS, software. Then, of course, the profile must be well executed in the lab, using an appropriately sized shaker, representative fixturing, and optimal control parameters. Finally, a sampling plan based on DFMEA, that's Design Failure Mode Effects Analysis, results that identify the principal vibration-induced failure modes can be used to develop an appropriate sampling plan, such as the one shown for fatigue, R99.95 in this case, C50, which stands for 99.95% reliability with 50% confidence. Note that the sampling plan begins with a minimum of 6 samples on test. While this is not always practical, depending on the product's cost and size, generally at least 6 samples are necessary to do any sort of useful statistics on the results. Attention has to be paid to a product's bathtub curve at the same time to assure that on the low end, we are not testing for so long that the materials simply wear out rather than failing as expected in the field. As different failure modes will be associated with different sampling plans, a single vibration test may have multiple sampling plans, starting with the most likely failure mode and decreasing the test repetitions as needed for that particular failure mode and any other failure modes that may be under consideration. For example, if the test is designed specifically for a solder failure, but a different failure occurs, an appropriate iteration of the sampling plan can be applied to determine if the product had already achieved the reliability requirement for that failure mode based on the sample size and repetitions. Please note that the sampling plan shown here is only for illustration, and that results will differ depending on the product, its intended service life, reliability requirements, and specific failure mode of interest. Because test duration, product hardware numbers, and lab equipment usage are well defined for success-run vibration tests, sampling plans enable optimal usage of available resources to minimize test time and cost. They're almost essential when supplying an OEM with robust parts on time that satisfy all performance, safety, and reliability requirements. As you can now see, sampling plans are an essential element in the product development lifecycle process. Conventional engineering thinking, and what most of us probably learned in school, is that a designed-in factor of safety is a good measure of robustness against failure. This is true for situations that are essentially static, have very few parts, known loads, and use materials that have well-known SN curves. The factor of safety is single-valued, theoretical, yet practical and highly deterministic in nature. For those situations, the factor of safety concept as defined by material ultimate or yield strength divided by a known stress level is probably satisfactory. However, for the rest of us who work on components or systems with lots of different materials, numerous interfaces, and highly variable cyclic loading environments, a deterministic approach to predicting failure is insufficient. The world of accelerated vibration testing for real-world usage is widely variable and stochastic in nature. A different approach is necessary to predict product reliability. Mathematically, reliability can be expressed as the convolution of the stress and strength distributions, as will be described in the next several slides. The convolution of two functions, f of x and g of x, is defined as the integral shown here of f of t times g of x minus t dt from minus infinity to infinity. This is a sum of the overlaps of one of the functions and all the shifted versions of the other function. When stress exceeds strength, a failure will occur. We refer to this convolution as stress-strength interference, where the stress arises from actual usage in the customer environment, and strength is the resistance of the design to a particular failure mode, say fatigue or wear, that is the result of materials used, manufacturing variation, inherent defects, etc. Stress, which we call f of x, and strength, which we call g of x, are distributions, which, when convolved, produce a representative distribution of failures as a function of time, miles, cycles, or whatever unit is used to represent usage. As said before, reliability can be expressed mathematically as the convolution of the stress and strength distributions, as will be described in the next several slides. To perform the convolution, we'll need to identify the statistical properties of both of these distributions, for stress and for the strength, so we have the parameters that we need to put into our program. But first, let's talk a bit about the statistics that are commonly used. Although many distributions can be used for this process, or to represent failure rates, the Weibull distribution has such plasticity to cover a broad array of circumstances that it is commonly used and will be what we describe in this webinar. The Weibull distribution is a special case of the exponential distribution and is a useful way to model time, distance, cycles, etc. to failure. We use it to model both the stress and strength distributions. For a two-parameter Weibull distribution, the probability density function is given as f of x is equal to beta over theta times x over theta to the beta minus 1 power e to the minus x over theta to the beta power. So that is really a mouthful. So theta we call the scale parameter, and we also call it the characteristic life, meaning it's the time at which 63.2% of the parts have failed. And that arises from the fact that it's an exponential distribution. Beta which we call the shape parameter, or more commonly we refer to it as the Weibull slope, is directly related to the failure mode. So every failure mode has a unique Weibull slope. And of course, f of t has to be greater than or equal to 0. You have to have more than 0 failures. You can't have less than 0 failures. The slope is positive, and so is the characteristic life. The Weibull distribution can be linearized to make a common form of Weibull graph that has unreliability, that is 1 minus the failure rate expressed as a percent, on the vertical axis, and time, which could be cycles, hours, miles, etc., to failure on the horizontal axis. This is shown in this top graph for 3 different Weibull slopes, every failure mode having a unique Weibull slope. So one failure mode might have a slope of 3, another one might have a slope of 1, another one might have a slope of 0.5. And making this into a linearized graph makes it easy to read and to understand. The bottom graph is really the same thing, except now it's not linearized, and it shows the probability density functions for the 3 versions in the top graph. You can readily see the adaptability of the Weibull distribution. The Weibull slope of 3 is, for all practical purposes, a normal distribution, while the Weibull slope of 1 is the exponential distribution. Slopes less than 1 generally have a decreasing failure rate as a function of time, miles, cycles, etc., whereas Weibull slopes greater than 1 have an increasing failure rate. Let's work through an example of how to develop a sampling plan. For our example, let's imagine that we have relative damage numbers that represent 20 customers over the service life of our product, and that we want a success run sampling plan for a vibration test that is designed to demonstrate R 99.95 C50, in other words, 99.95% reliability over the service life with a 50% confidence level. 99.95% reliability over the service life basically means that we're willing to accept 5 failures out of 10,000. So there are 4 steps to this process. First step, we need to estimate the Weibull parameters for the stress distribution using the customer relative fatigue. Because remember, we're going to eventually convolve these 2 distributions, and we need their parameters. So step 2 is to set the Weibull slope for the strength distribution. And for our example, we're going to use beta equal to 3 as a generic representation for a fatigue failure mode. In step 3, we have to back calculate the characteristic life, that's the theta parameter, for the strength distribution by convolving with the inputs from steps 1 and 2. Then step 4 is to use the resulting value for strength characteristic life with the Weibull success run formula to establish a sampling plan. So just to recapitulate here, right, we need parameters for our customer distribution. So we have the customer data, and from that we can calculate the slope and characteristic life for our customer data. We need the same thing for our strength data, except now we need it such that there's a defined amount of overlap, and that amount is defined by whatever reliability we set it to. So the slope is driven by what the failure mode is, and we need to know, well, what characteristic life do our parts have to achieve to get to a set amount of reliability. So in step 1, we estimate the Weibull parameters for the stress distribution using our customer data. So first we list the 20 customers along with their relative damage numbers, which I've done here. These numbers are then ranked from smallest to largest, and the respective median ranks are calculated using the given median rank formula. So median rank, maybe a new concept for a lot of people, but basically we can take the rank, so we arrange these numbers from smallest to largest. So looking at the column here, the largest number in here is 0.102, and the smallest, which would be number 20, is 0.884. So the range from smallest to largest, and we calculate their respective median ranks by taking the rank. So that's J. So in this case, I would take 17 minus 0.3 and divide it by, there are 20 samples in this plan, plus 0.4. So we calculate all of the median ranks and list them accordingly. Next, we take this data and we make a linearized Weibull plot by graphing the natural log of the customer relative damage numbers against the natural log of 1 minus the median rank. So we took our data to get the x's and y's here, the horizontal and vertical axes, in a linearized fashion. And once we have that, we can then fit this data to a least squares regression best fit line and read off of that the Weibull slope. Using the value for the intercept, we can then estimate the characteristic life theta, which mathematically works out to be e to the minus intercept over Weibull slope. So remember that the characteristic life is the time, miles, cycles, etc., at which 63.2% of the parts have failed. So we have our best fit line, and for this particular data set, our correlation coefficient is 0.9511. So that's a pretty good match. It's a pretty good correlation. And we have the Weibull slope here of 2.2508 and an intercept of 1.2663. And we use that intercept then back into our Weibull function to calculate a characteristic life, in this case of 0.57. Remember, these are all relative numbers, so don't try to read anything absolute in them. They're just relative. So often, quite often, measured customer data is not available. In that case, pseudo customer data can be obtained from proving ground measurements or lab measurements, surrogate data from similar applications, virtually synthesized data, or other sources. These data could then be used Monte Carlo fashion to develop a distribution of customer usage that we can then use for developing our sampling plan. All right, great. Now we have estimated Weibull parameters for the stress distribution, but we still need to get Weibull parameters for our strength distribution so that we can perform our stress strength convolution. So to do that, we're going to do a back calculation. With the stress, in steps 2 and 3, we're going to get the stress distribution. To do this, we need to assume a Weibull slope, a beta, for the failure mode of interest. We'll use beta equal to 3 as a generic representation of a fatigue failure mode. So then we have to use a convolution routine, and you can make one using R or Python or even Excel to back calculate a value for strength characteristic life, theta, such that the stress and strength distributions overlap to equal the desired failure rate, which of course equals 1 minus the desired reliability, which for our example is 1 minus 0.9995. You can see in the table that several attempts were made, starting with the guess of theta equal to 2.3. So we started here. Our target reliability is 0.9995. We assumed a strength slope of 3, and we just took a guess. We said, let's let the characteristic life be 2.3. And then we did our convolution. We came up with the probability of failure of 0.0177365, which means 1 minus that for reliability is 0.9822635. So we're a little bit short here, right? We're aiming for 0.9995, but we're only at 0.98226. So we're off by 0.0172. So we take another stab at it. We try characteristic life of 3.1. Getting a little closer. Now we got 0.9926. So we up it a little more, 4.2, and then 4.8, 5.5. And finally, we walk up and converge as 7.4 to be a reasonable strength Weibull characteristic life that, with our customer data involved, will give us a target reliability of 0.9995. We'll hold on to this value for step 4, but first we have to digress for a moment to talk about the standard binomial success run formula, which in turn will be used to develop the Weibull success run formula. The binomial probability density function is given by the formula probability of a failure or an outcome is equal to n factorial over n factorial n minus x factorial p to the x power q to the n minus x power. That's a binomial probability density function. N is the number of samples on test. P is the probability of failure, which in this case we can get from whatever we set our reliability target to. Q is the complement of P, so in other words, the probability of not failing. And X is the number of failures that we would see on the test. The binomial probability is appropriate when following conditions are satisfied. First of all, we have to have a fixed sample size, which in our testing situations we do. Our samples are independent, which is also true. Only outcomes are splitting our world into either failure or not failure. So we don't have partial failures. It's either failed or it didn't. And the probability of a failure is constant. So probability of a failure on a given product for a particular failure mode, we assume to be constant, and we set it equal to 1 minus our desired reliability. So this is exactly what we have and what we need for a success run testing situation. Note that because the binomial distribution is discrete, we can use a summation to calculate cumulative binomial probability. So in that case, we just sum from 0 failures up to however many possible failures we can have, how many samples we have on the test, and we plug it into our binomial formula, and we add those together, which works because they're independent and discrete. So we can add those together to get our cumulative binomial probability distribution. So this would tell us the probability of one of our parts failing during test if we know, in general, the probability of a part failing. We assume this to be our failure rate, or 1 minus the desired reliability, whatever our reliability target is. For our purposes, we will define confidence level as C is equal to n minus x. The number of samples on test that did not fail. In our example, we will set C equal to 50%. So we want 50% confidence, or 0.50, which is commonly done as 50% confidence in this context equalizes the producer's risk. So that would be producer doesn't want to overestimate reliability. And it balances it with the consumer's risk, because the consumer doesn't want us to underestimate reliability either. So we use 50% typically for that purpose. So the complement of C, our confidence level, is the number of samples on test that did fail, which is equal to 1 minus C. If we let P equal 1 minus R be the probability of a sample failing, and let Q be the complement of P, which is the probability of no samples failing, then Q is equal to 1 minus R is equal to R. So if we followed all of that, then we can substitute those values into the binomial probability distribution and express the cumulative probability as 1 minus C is equal to the sum x equals 0 failures to our number of samples times the rest of the binomial probability distribution formula. From that, we can develop what we call the binomial success run formula. Success run testing means that 0 failures are allowed. So we're going to run this test, and we'll say that we met our reliability requirement if at the end of the test, we didn't have any failures during the test or when we're all done with the test. So we set x equal to 0 in our binomial probability distribution. And here's what happens, right? So if I don't allow any failures and I accumulate my binomial failure distribution, right? So now n factorial over 0 factorial, 0 failures, over n minus 0 factorial, or 1 minus r to the 0 power r to the n minus 0, right? So we get n factorial over n factorial, which cancels. And anything to the 0 power is 1, so that's 1. And we end up with 1 minus c is equal to r to the n. So our question is, how many samples do we need? So we need to solve this equation for n, which we can do by taking the natural log of both sides and then isolating n by itself to get our sample size for our success run formula is equal to the natural log of 1 minus our confidence level divided by the natural log of our desired reliability. So that tells us how many samples we need to test without failure to one product service life to demonstrate a given level of reliability. The problem is, if I do that, n is too big. So if we look at our example, we can say that, if we have R99.95 C50, we would need a lot of samples. That would work out to 1,386 samples that we would need to put on the test to one service life. This is not going to happen. So let's look at our previous Weibull math and see if we can combine these distributions to help us generate a more achievable number of test parts and test time. Looking at the Weibull distribution again, we can recall that the probability density function for the two-parameter Weibull, which gives the probability of a failure as a function of time, distance, cycles, etc., was given by f of x is equal to beta over theta, x over theta to the beta minus 1, e to the minus x over theta raised to the beta. That's the same formula that we started out at the beginning of this webinar. Accordingly, the cumulative density function gives the probability of x number of failures over an interval. So now we're doing this over an interval of time, distance, cycles, etc., and is found by integrating this Weibull probability density function. So I've written that out this way. And I left out the lengthy details of performing this integration. If you need help with that, just let me know. But it works out to be 1 minus e to the minus x over theta raised to the beta power. So finally, the cumulative reliability function, which is the complement of the cumulative Weibull, r of x is equal to 1 minus the result of this integration, which is 1 minus 1 minus e to the minus x over theta to the beta, which in the end just boils down to e to the minus x over theta raised to the beta. So the Weibull slope and characteristic life and number of failures gives us the reliability. So now we have a solution because we can put together the binomial and the Weibull to come up with a Weibull success run formula. And so to do that, just remember that we said that 1 minus c is equal to r to the n from our derivation of the binomial success run formula. And we can rearrange these terms, not to solve for n, but to solve for r, which gives us 1 minus c raised to the 1 over n power. N is the number of samples we're going to put on the test. If we equate this reliability expression with the Weibull cumulative reliability function that we derived earlier, we can solve for x. And x will represent the number of lives we need to go, or number of service lives we have to test to without failure, ultimately. So equating our two equations, so e to the minus x over theta to the beta is equal to 1 minus c to the 1 over n power. And if we work through the math, we're going to take the natural log of both sides. And then we recall that the natural log of something raised to a power is simply equal to that power times the natural log of the something. So I end up with ln 1 minus c over n. I move this minus sign to the other side. I take the beta root of both sides, and then I can multiply by theta. So I end up with a formula that we can use to optimize the test time, lab resources, and have statistical confidence in the meaning of the test with respect to reliability. So let's see how this worked out for our example. So in our example, and I did this actually for 3 different situations, You can see that we calculated Weibull success run sampling plans for R99.95 C50 for fatigue, R99.5 C50 for fatigue, and R99.95 C50 for wear. And we did this just to illustrate the effects of changing some of the parameters. For the wear failure mode, we assumed a Weibull slope equal to 2 for our strength distribution and subsequent back calculation for wear characteristic life. We can see that higher reliability requires longer testing, which probably is not a surprise, right? Just going from R99.95 to R99.5, so just changing that third digit from a 9 to a 5, causes us to, if I just look at 6 samples on test, for example, at 3 nines and a 5, it's 3.6 service lives I have to test to. At 2 nines and a 5, it comes down to 1.7. Likewise, reducing the Weibull slope as we did for wear significantly increases the test length for a given durability, given reliability. So for wear, for 3 nines and a 5, 6 samples, right, and compare this 3.6 service lives to 9 service lives. So we can see the effect here of changing our failure mode or changing our sample size. And we do need to be very aware of a few things in the bathtub curve, right? So if I have 6 samples I'm looking for wear, I'm going to go to 9 service lives without failure to demonstrate a given reliability. We have to ask ourselves whether or not it's reasonable for any part to survive without failure to 9 service lives. So what that's basically saying is that if I'm trying to demonstrate wear, I really do need a fairly large sample size to do that realistically. So these are sampling plan examples, and it all comes down to really this Weibull success run formula that we derived here, and back calculating a characteristic life for a given reliability strength distribution overlapping a customer usage distribution. So now you know about vibration sampling plans and why you need them. Identifying real failure modes for the correct reasons is essential for effective use of product development resources. For vibration testing, this means having the right data measured properly and correctly analyzed to correlate an accelerated test or virtual twin to a known amount of severe customer usage. With the right tools and know-how, the process to acquire good data and use it to arrive at a vibration test profile with the appropriate frequency, content, amplitude, and duration is readily achievable. Vibration research hardware and software gives test engineers confidence that their test profiles deliver field representative results. Developing a sampling plan and using it to optimize test hardware and lab equipment scheduling can save time and money while assuring confidence that your product will exceed your customers' reliability expectations. Appropriate use of the success run formula to make vibration a sampling plan ensures that your product is truly ready to release to commerce. So that completes our webinar about vibration sampling plans. As you can see, we're laser focused on vibration testing, and our products have an unmatched set of tailorable capabilities. You can use the floating question button on the screen to send an email with any comments or questions you may have about vibration test sampling plans or vibration research products. We're here to help, so please contact us if you have any questions, and we'll be sure to get back to you. Thank you for listening, and have a great day.